Design ChatGPT from scratch. Agentic AI World Interview Prep, Episode 10. Welcome back to Agentic AI World, your daily interview prep podcast for AI and software engineering roles. I'm your host, and today we're doing a deep dive into one of the most common system design questions you'll face in senior AI engineering interviews. How would you design ChatGPT from scratch? This is a big one. Let's break it down. Part 1. Clarify the scope. Before you jump into architecture, always clarify. Ask your interviewer, are we building the training pipeline, the inference layer, or the full product? What scale? Millions of concurrent users? Billions of tokens per day? Do we need real-time streaming responses? Multi-turn conversation support? Safety filtering and content moderation? Assuming we're designing the full product end-to-end, let's go. Part 2. High-level components. A system like ChatGPT has 5 major layers. 1. The model layer. This is your large language model, transformer-based, trained on massive corpora, fine-tuned with RLHF, reinforcement learning from human feedback. The model itself is the brain. For inference at scale, you'll use model parallelism, splitting the model across multiple GPUs, and optimizations like flash attention, quantization, and speculative decoding to keep latency low. 2. The inference service. When a user sends a message, a request hits your inference cluster. You need horizontal auto-scaling here. NVIDIA Triton Inference Server or vLLM are common choices. vLLM in particular is great because of its page attention mechanism. It handles KV cache memory efficiently, which is critical for long conversations. 3. The conversation state layer. ChatGPT maintains conversation context across turns. You store conversation history in a fast key-value store. Redis is a great fit, keyed by session ID. For each request, you retrieve the prior turns, prepend them to the prompt, and send the full context window to the model. You need to handle context length limits gracefully, either truncate, summarize, or use a sliding window approach. 4. The streaming gateway. Users see tokens streaming in real time. This is handled with server-sent events, or SSE, over HTTP. Your API gateway, Jinx or Envoy, maintains long-lived connections with clients and streams tokens as they're generated. You must design your service to support backpressure so slow clients don't overwhelm the server. 5. Safety and moderation layer. This is non-negotiable. You run a content classifier or a small fine-tuned model on both input and output. Inputs are checked for harmful prompts, jailbreaks, and policy violations. Outputs are checked before they're streamed or after, depending on latency tolerance. OpenAI uses a combination of rule-based filters and learned classifiers here. Part 3. Data flow. Let's trace a single request. User sends message, API gateway auth service verifies session rate limiter checks quota load balancer routes to inference service context store fetches conversation history. Prompt is assembled with system prompt, history, and new user message LLM generates tokens stream back through SSE safety, filter runs in parallel response stored in conversation history, tokens land on user's screen. The key insight for interviewers. Every step must be designed for low latency. The P99 time to first token should be under 500 milliseconds. That means fast context retrieval, warm model replicas, and an efficient tokenizer. Part 4. Scaling challenges. Here's where you demonstrate senior-level thinking. Challenge 1. KV cache. Transformer attention is quadratic in sequence length. Long conversations are expensive. Solutions include sparse attention, sliding window attention, or summarizing old context using a smaller, cheaper model. Challenge 2. Hotspots. Popular conversations create hot paths. Your Redis session store must be clustered with consistent hashing. Inference workers can't be stateful. The load balancer must be session agnostic or sticky at the gateway level only. Challenge 3. Model updates. You can't just swap the model. You need blue-green deployments at the inference layer. Route 5% of traffic to the new model, monitor quality metrics, then scale up. Challenge 4. Cost. LLM inference is expensive. Use spot instances for batch workloads, preemptible GPUs for non-real-time tasks, and request batching in vLLM to pack multiple user requests into a single forward pass. Part 5. Monitoring and Observability. Great engineers always talk about observability. You track TTFT, time to first token, target under 500 milliseconds. TPS, tokens per second per GPU. Error rates, model errors, timeout errors, safety blocks. Conversation length distribution helps forecast costs. User satisfaction signals, thumbs up or down, session length, re-engagement. Use OpenTelemetry for distributed tracing. Your inference service, safety layer, and context store should all emit spans so you can pinpoint latency bottlenecks. Summary. To design ChatGPT from scratch. Model layer with efficient inference, vLLM, speculative decoding, quantization. Stateless inference workers behind a smart load balancer. Redis-backed conversation state with sliding context windows. SSE streaming gateway for real-time token delivery. Parallel safety and moderation pipeline. Comprehensive observability with TTFT and TPS metrics. Nail these 5 pillars, and you've answered the question at a senior engineer level. That wraps up today's episode. If you're prepping for your next AI engineering interview, subscribe to Agentic AI World, and you'll get a new topic every single day. Tomorrow we'll be starting a fresh cycle, so stay tuned. See you tomorrow. Keep learning, keep building.